Well, we need to integrate this one here. We know our derivative of this, and we need to find y. Well, if your derivative is this and you want your original function, you basically need to integrate this. So if you integrate the left side, you're going to get your y. Integrate the right side, that's what we have right here then. Well, how do we go about integrating something like this over here? Well, we could take a look at your sine, or not sine, sorry about that, natural log of x. Well, we could say u is the natural log of x. You might be wondering, why did I say u should be the natural log of x? Because I know the derivative of the natural log of x is my 1 over x that I have shown up there. So I get then, oh, I need to have a dx hanging around here on this one. So what I have, instead of having this, I then really have a du. And instead of having this, that's really my u. So I really have, okay, by the way, I got an extra du hanging around because that's a du here on the top, so just ignore that for right now. So it's really just, we'll put a 1 here on top, 1 over a du, or 1 over u du. So it's really just natural log of u plus c when you integrate. Substitute in what u is, and we get this. U was, once again, the natural log of u. So y is really the natural log of the absolute value of the natural log of x plus c. Here we have some more integration formulas. These formulas are the integrations of our trig formulas. Our 6 basic trig ones, you integrate them, these are what you get. Just go ahead and plug these in your memory so that you can work with them at another time. So, you're asked to now integrate a definite integral from 0 to pi over 4 of the square root of 1 plus tangent squared. Hopefully you remember 1 plus tangent squared is really a secant squared, and so you have the square root of a secant squared, which is a secant. You might be wondering, where did that thing right here come from? Well, that goes back to your trig class, one of your Pythagorean theorem identities that you were supposed to have memorized back then and hopefully still do. Now, all we have to do here is integrate our secant. Well, what we have up here is the integral of secant. That goes to natural log secant u tangent u plus c. In this case, x is your u. Well, so that means we just use that formula. We plug stuff in, natural log of secant x plus tangent x. Then we got to evaluate that from pi over 4 to 0. So you plug in your pi over 4, secant pi over 4 plus tangent pi over 4 after your log, minus natural log, plug in your 0. Secant 0, tangent 0 is 1. Well, that's your exact answer. You could do the decimal approximation, and you would get this. We also have average value. Average value was covered in section 4.4. This is your average value formula right here. We want to find the average value of our tangent function on 0 to pi over 4. This is your A, this is your B, so it'd be 1 over your B value minus your A value. Your integral from your A value to your B value of your function. Well, integral of tangent. We should be able to do that. Notice in front here we get 1 over pi divided by 4, but instead of having a fraction of 1 divided by a fraction, you multiply by the reciprocal, because instead of dividing by pi over 4, you multiply by 4 over pi. Integral of our tangent of x. Well, With that in mind, we're going to want to just go ahead and say, oh, integral of the tangent of x. Oh, integral of tangent of x, and we'll just use our formula right here. So this is one of the plug and chug problems. You find your formula, you plug it in, you chug on through to the answer. Now, we don't need to have a plus c for our problem because we're dealing with a definite integral. Now we need to evaluate that. The negative we could pull out in front with this. Then you got to take your pi over 4, plug it in here, cosine pi over 4 after your natural log, minus what you get when you plug in a 0. Natural log, cosine of 0, which is a 1. Well, we then get this. Remember, the natural log of 1 is 0 because it's e, your base is e. E to what power is 1, and that is 0. So subtracting 0 doesn't change it. So this is your exact answer, and your decimal approximation is right here.